Our project for the Math Expo is Data Exploration by Jonathan Capillion,
Michael Haratunian,
and Yadi Kekriotis.
First, underneath the title, we have the original data table that was given to us with the heights of the 24 third graders to the nearest inch. We calculated the mean of the data by adding up all the data points and dividing by the number of how many data points there were. This came out to be 53 1/3. With that mean, we needed to find the standard deviation, and to do that, we started by subtracting the mean from the data points. Using the differences between the means and the data points, we took the absolute value, the difference away from 0. From those differences, then squared them. For example, 55 equals the absolute value of 1.67 squared, which came out to 2.79. We did that for all 24 data points. Then with the numbers with the square differences, we get the sum of all those, and then with keeping the number in our head, divided that number by the number of points minus 1. So in this case, 24 minus 1, which is 23. If we just divided by n, which in this case is 24, we would be underestimating the real population variance. Dividing by n minus 1, in this case 23, allows for a more accurate approximation of the population variance. So we divided 68.04 by 23, which came out to 2.958. This is the population variance. Then we took the square root, which is 1.63. A histogram is a type of frequency diagram. A frequency diagram graphs the number of occurrences of each value. So this histogram doesn't mean their heights are 1, 2, 4, and 6. It means that the heights of 53 showed up 6 times, for example.
The sum of the deviations from the mean of any data set is 0. The function s of x equals negative yx plus yx reinforces the idea that the sum of the deviations below the mean will always equal the sum of the deviations above the mean. As previously mentioned, a step to finding the standard deviation of a distribution is to square the differences between the data point and the mean. These unsquared differences are known as the deviations from the mean. The deviations are squared because of this truth that the sum of the deviations is 0. If the deviations were not squared, then the standard deviation would be found through taking the square root of 0 divided by n minus 1. The result would be 0 and would create an invalid standard deviation since not all the data points are equal to the mean.
A large part of our problem focuses on sample distributions. A sampling distribution is a data set of values derived from taking samples of another population. The values are most frequently means and sums, but medians and modes can be sampled for as well. Each value in a sampling mean distribution represents the mean of a sample taken from an underlying population. The central limit theorem states that for any data set, after taking enough samples, the sampling distribution will be normally distributed.
The mean of a sampling mean distribution will equal the population mean because if a sample size of n is taken from a population x, then the average of the means of each sample size of n will be equal to the mean of x. This is stated by the central limit theorem, that the mean of the means of an n-sized sample will become normally distributed, having the same mean as the population mean. If one sample with size n is taken from a population, there will be a low probability that the sample and population means will be equal. Each time another sample of size n is taken, however, the probability of the means being equal will increase since there is a higher chance that a point closer to the mean will be chosen in the sample. The central limit theorem also states that as more sample sizes are taken with a greater value of n, and as each of the means of their means are plotted on a graph, the sample graph will have a smaller variance than the population graph. A low variance indicates a small standard deviation, or by how much the data varies from the mean. The higher the sample size, the higher the chance that the sample mean of the chosen data points will be closer to the population mean. In other words, If more sample sizes are taken that consist of more data points chosen, there will be a larger probability that those points chosen from the population in the sample will be ones that are closer to the mean. If they are closer to the mean, then the average of this multitude of close sample sizes will become even closer to being equal to the original population mean. When this is tested through a computer program, since the computer could test with much greater precision, this is exactly what occurs. The graph made by the computer program will show that the sample graph has a skew in kurtosis closer to 0 than a sample graph with less samples taken of a lower sample size. Skew and kurtosis are two components that represent a normal distribution more closely.
Skew is the amount of asymmetry in a dataset distribution, so as the skew approaches 0, the dataset distribution becomes more perfectly symmetrical about the mean and therefore closer to normal distribution. Kurtosis, however, is how sharp the peak in a distribution is. If there is positive kurtosis, the peak is sharper and the tails are fatter. If there is negative kurtosis, the peak is broader and the tails are smaller. A perfectly normal distribution has 0 kurtosis.
Therefore, with the computer program that will be shown, the central limit theorem indeed holds intact. The two equations that can be derived from the central limit theorem have been displayed on our poster.
The first is that the mean of a sample mean distribution is equal to the population mean. The second is the standard deviation of a sample mean distribution is equal to the population standard deviation divided by the square root of a sample size. Now we will head over to Yanni at the computer program.
Take it away, Yanni.
To demonstrate the relationships derived from the central limit theorem and the other topics we have talked about in our presentation, we wrote a computer program that creates a random dataset and then takes samples until the sampling distribution has the same mean as the original population. The program also shows how a larger sample size results in lower variance in a sampling distribution, with a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. First, I'll run the program at a low speed and show how the sampling distribution approaches a normal distribution over time. As you can see, the sample distribution is becoming more and more normally distributed. Now, I'll make it so the program stops once the mean of the sample distribution and the mean of the population are equal. Here I will run the program with a low sample size and a higher speed so the normal distribution is generated more quickly. As you can see, the data is much more widely distributed because with a small sample size, the samples have a lower chance of having points chosen that are close to the population mean. And now the data has stopped as the means are equal between the population and the sample data. Next, I'll run the program with a larger sample size to demonstrate how the standard deviation changes. As you can see, the data is much more concentrated around the mean, meaning that it has a lower standard deviation / variance, which is shown at the left. Finally, if I run it with a very high sample size, the sampling distribution will barely vary at all. And that is our computer program.
This now concludes our Math Expo presentation on data exploration. Thank you for watching!